Yes. The floor is yours.
Got it. Yeah. Yeah. Thank you for this introduction, and also for the opportunity to give a presentation, particularly this large audience in Memelo. I will share the screen now and give my presentation. Okay, there's still something in the image. Yeah, okay, now.
Yep.
So I will talk about metals under microstructural evolution, followed in situ by synchrotron and neutron radiation. As Eric has introduced, I'm Klaus Liss, and I'm an honorary professor at the University of Wollongong. So this is a picture of Wollongong, and the university is behind. That's a little south of Sydney, for those who don't know. But at the moment, I'm spending a week in Broken Hill, which is 1,300 kilometers away from Wollongong in the Australian outback. So I'm suffering already the desert temperatures here. The overview of my talk is given here. I will briefly introduce neutron and X-rays and in situ studies. And I thought today's topic, I will concentrate on magnesium. So I give examples of applications of neutron and synchrotron X-rays on magnesium. So we do, recently, I'm writing a paper which is not published yet on magnesium AZ31, where we did microbeam diffraction after high pressure torsion. Also, 1.5 years or 1 year ago, we published a paper on phase and microstructural transformation of magnesium AZ91, together with AZ31, but here I want to focus or give some complementary insights on AZ91 using monochromatic X-ray diffraction. And then I come to a new technique, namely the wide beam Laue diffraction, talking about abnormal grain growth. So this is a different method, as you will see, which is very unusually, but we can look to grain reorientations and see grain rotations during this grain growth. So I think now I can scribble on the screen. This is one of the neutron facilities I used in the past. So the J-Park Materials Life Science Facility. And I want to come directly to one of these magnesium experiments. So what we have there is a dilatometer furnace. The beamlines there, many of you probably have seen beamlines. There's a source here, and there are beams coming out of this source, and the hut and experimental setup is called a beamline. So what they have there is a heated load frame or a dilatometer. So here to the right is a dilatometer furnace, which I have used. And the particular onset of I'm thinking I missed some introductory slides. Anyway, I go ahead then here. We have an incoming neutron beam coming from the top and hitting a sample which is oriented under 45 degrees. And then we look on scattering angles in the radial direction. So this is the in the radial direction, in the rolling direction, or in the transverse direction. So the detector to the right measures lattice planes as aligned here by the green, while the detector to the left measures the lattice planes with a normal, so the scattering vector along the rolling direction. So we get probes along the normal direction and the rolling direction. This leads to those diffractograms here, namely in the scattering vector parallel to the rolling direction and scattering vector, sorry, perpendicular or parallel to the normal direction. And we see the typical fingerprints of magnesium HCP material. We see here the reflections as indexed at the bottom. So we have the 100 reflection, the 002, the 101 reflection, and so on. We ramp the temperature as a function of time. So the time is given here to the left, and I often show these kind of diffractograms, while the temperature is risen, temperature is given there, is risen, then we hold it, and then we furnace cool it down. So the two detectors, they show these diffraction patterns as a function of time. And we see already, basically all the lines are there in both of the detectors. However, there's some difference. For example, here, the 100 reflection of magnesium is very strong along the rolling direction, while it's very weak along the normal direction, and vice versa for the 002 reflection, so for the basal plane reflection. And this is because of texture. We know the rolling texture typically has this basal texture where the lattice planes, the basal planes, 001 planes, are aligned parallel to the surface of the sheet material. So if they are parallel to the sheet of the material, that means the normal direction, scattering vector in the normal direction, is parallel to, describes planes parallel to the surface. And if the basal planes are aligned all parallel to the surface, then the 100 planes, they have to be perpendicular to it. And that's what we observe here. So you see here at the bottom, the 100 reflection is very, very weak, but it scatters a lot into the rolling direction detector. So they're pointing more into the rolling direction. And then we can go through the other reflections. What we see already in this figure is that we have, as we raise temperature, peak shifts. So the peak shifts somehow look like the rising temperature. Go up in temperature here from 300 to 600-700 Kelvin. And we see there's also a shift which looks very much like the temperature profile. As we have thermal expansion, the lattice parameter becomes larger, means in reciprocal space, we get a shrinkage. So we get shorter scattering vectors. So we're going closer to the 0 here on the x-axis. Then we can plot, oops, something jumping. Then we can plot the lattice strain. So we normalize to the value at 300 Kelvin as a function of temperature. And we get these straight lines. The only not so beautiful thing in this experiment is we have some experimental temperature lag, which lags, the reading lags behind what we expect to have. And therefore we have a temperature error. But if we look to the slope of the material, to the slope of this lattice strain, then we see it's all parallel once the temperature is in a constant increasing or decreasing rate. And from there, we can evaluate the slope, which is the expansion coefficient. So the coefficient of thermal expansion, evaluating here to 31 times 10 to minus 3, 10 to minus 6 per Kelvin. Particularly, I want to point out, it looks very straight. There are no anomalies. Also, if I plot it for many of those reflections, they all superimpose. The strain superimposes. That means the strain, so delta L to L, or delta D to D, or delta Q to Q, minus delta Q to Q, where Q is the position of the peak. They superimpose. So thermal expansion is the same for all reflections. That means it is isotropic within the accuracy of this measurement. And this is an exception or a coincidence in a hexagonal crystal system, because a thermal expansion tensor in a hexagonal system can have two independent components, namely parallel to the z-axis and perpendicular to the z-axis. So by coincidence in magnesium, and that has been found in literature already maybe 60, 70 years ago, thermal expansion is isotropic. Let's look to the peak width here. We can see that the width, the full width half maximum of the peaks, they go down as we heat up the material. So we come here from the top, and then we go down as we heat until we reach this ultimate value, heat, and then we cool, and we keep basically constant. That means we have some recovery of the material. We can do the Williamson-Hall plot. Williamson-Hall says the delta G, so the peak width here, vertical, is some 2 pi over the size of the grain or the coherent scattering volume times the shape factor, which is close to 1, or 0.9 or whatever, plus the strain gradient times the position, so the x-axis, which is G here. So the delta G is the vertical, and the G is the horizontal axis. And if we plot all these peak widths, we can regress a linear function. So in the most simple way, it is this equation where we have a linear dependence and a constant describing the grain size. So here on heating, as said already, we have a decrease of the peak width. This is due to recovery. So we start with this line and we end with the blue line. And we can say, because there's no change going back down, the blue line is close to the instrument resolution function. The red line is what is in excess of the instrument resolution function. And if we evaluate this equation, then we get axis offset, which is relatively small. So we're talking very large grains in the micrometer range, where this method is not really suitable. But we can see that the strains recover. So stresses, internal stresses, strain gradients, they recover. And they amount, so we see at the top here is 4 times 10 to minus 3, and here 3 times 10 to minus 3. So the difference is about 1 times 10 to minus 3. Meaning at the beginning we had stresses, or not stresses, strains in the order of 10 to minus 3. Now I like to take the same material and do some high pressure torsion. So high pressure torsion is a severe plastic deformation process, which is shown here. We put the material between two anvils, and the one, in this case, the lower anvil, rotates against the upper anvil. This is together with Megumi Kawasaki, who is a professor at the Oregon State University in the US. Then we take the material and put it into the beamline, high energy beamline P21.2 at the DESI in Germany. So here we have a furnace. We put a small piece of sample, only a few millimeter in cross section. And then we have two detectors. We have one detector which is a little bit closer, short camera length, and we have a long camera length for having either more coverage here in reciprocal space, that means more rings, or higher resolution on less rings. Here are diffractograms, or part of the diffractograms recorded by the two detectors. So to the right, we see that we have continuous rings, and the right is this detector which is closer, so the rings are shorter because we have cones. They open in space. As we go further away with the same scattering angle, the cones, they open. They become larger. The rings become larger if you go further away, just a geometrical projection. But what I show here, to the right, we have a temperature. This is taken at this time, 104 seconds, and temperature 320 Kelvin. We have smooth rings. So the rings, they're continuous. They may have some texture, but they're continuous. While at 445 Kelvin, we can make out spots, dots on the rings. And this is due to grain growth. So actually, we had a microbeam here, 6 by 3 micrometer in size, and we can resolve these spots, single grain reflections. So here, these little dots you see on the Debye ring. I hope you can see them, which correspond to grains in the 160, 170 nanometer range. So this is very small because we work with very ultra-fine grained material. On the right-hand side, the grain is not much smaller. I've emphasized a few here. So we see continuous rings here at 104 seconds or 320 Kelvin, also in the other detector, 120 Kelvin. Then 445 Kelvin, we see already that spots are plenty. And they coarsen, the distribution of the spots, they coarsen as I go longer in time and higher in temperature. And this is due to grain growth. We also can estimate the grain size from the distribution of the spots on the rings. We can count how many spots we find on one ring. So if we have isotropic distribution in orientation space, then we can estimate the number of grains in the illuminated volume, doing a little bit of crystallography and also considering the mosaic spread. That means how sharp a line is. If a line is not that sharp, it spreads out in reciprocal space. So then we get a distribution. So as here, you see here, oops. Yeah, there is a distribution, not just one spot, but many spots. And those are low angle grain boundaries. So it's one grain, but it has some mosaic spread. And that washes, blurs these diffraction rings also in reciprocal space. Good. So we can do the radial and the azimuthal distribution on these two-dimensional diffraction rings. If we go radial, then we have the normal powder diffraction patterns, similar as in the neutron case. So we have the same reflections here as in the neutron case, and we can see how they evolve. They shift again because temperature goes up here. But eventually, because we have such a fine beam, we go into the problem of grain statistics, where the grain becomes large after growth, and we don't have all the time intensity diffracting onto the rings. So the crystal may be misaligned, and then we don't get intensity. So as you know, as powder diffraction people know, if grain size becomes large, we would not have a good powder diffraction pattern. But we also see here the peak width changes. We see the slope, and we see also there's a little bump in the slope. And here we see a second phase coming. Do you see that? There's a little streak coming out there, and it repeats here and there and there. And we can determine that to be an intermetallic phase, aluminium 12, magnesium 17, which we have not seen in the as-received material during the neutron experiment. Then we can look to azimuthal space, so going around the ring and reproducing the intensity for each time step here in a line. So we bend the ring straight, and we do that for the left detector here and for the right detector there. You remember we have two detectors. Well, what we see at the beginning, we have these smooth continuous rings. We see there is some distribution due to texture, but that's it. Eventually, we get a transition from continuous ring to this marble-shaped areas, marble speckled areas. And this is the recrystallization. So in this transition range, recrystallization takes place. And eventually here, we're still working in a two-phase field here, but eventually here, we are going to pure magnesium phase, and then we get a lot of grain growth, so a lot of coarsening on the diffraction rings. We can look to that into detail, but because of time, I have to hurry on. So this is the peak width for these many reflections here. I fitted these reflections. And then we can do the Williamson-Hall plots again. We start with the blue line. These are intermediate lines, and we end with the red line. We can look to the scatter. The scatter around these lines is due to these locations. So if we do it very well, we would need to apply the modified Williamson-Hall plot, where we look to the other anisotropic strain fields around the dislocation. But this in magnesium becomes very complicated because at different temperatures, you have different slip systems, and you have different Burgers vectors, you have different orientations to the slip plane and so on. So it becomes very difficult. But what we see here, the black ones in the time or in the process of recrystallization, they're aligned much better onto a straight line rather than in the blue or initial or in the final state. And this is because recrystallized grains, they are free of dislocations. They are supposed to be free of defects. Or of course, they're point defects, yeah, but supposed to be free of line defect and planar defects. So we have a good fitting here on a straight line during the recrystallization, and much later, after grain growth, we have the scatter again, and this is due to dislocations. And the scatter is different here at the bottom rather than at the top, because at high temperature, we have different slip systems activated rather than at low temperature. We can go there into detail, but I'm running out of time. So we can do the Williamson-Hall analysis, take our equation with the grain size and the slope, yeah, for the gradient of the lattice strain, and we see the slope decreases here, and the intercept also increases. And if this wouldn't jump all the time, I would be much happy. Right, so I'm sorry about that. We also can look to the peak shifts in thermal expansion. So we have the temperature here, and we have the total lattice strain. So this is thermal strain and chemical strain and whatever strains you have. We see that this is not linear. We can fit a linear function here at the bottom. So between 300 and 350, I fit it and get thermal expansion, and the thermal expansion is shown here at the bottom figure as a function of sine squared psi. So as a function of orientation of the lattice plane or the reciprocal lattice vector. And we see there's not much systematic dependence. It scatters around the mean value, so we get 24.6 times 10 to minus 6 per Kelvin. But then, if we extrapolate this line here, the straight line, we get a bump. So I remove from the data the straight line and get this figure to the right here. So there I removed the 24.63 times 10 to minus 6 and get this bump in thermal expansion. Now I would say here above, let's say above 500 and something Kelvin, the grain statistics become poor, so we cannot fit the peaks very well anymore, as we have seen. You see there are peaks, the areas where peaks are missing, and so on, because of bad grain statistics. So we only can do that up to 500 Kelvin, but that's enough. So we can fit, for example, a Gaussian. I just tried and fitted a Gaussian there, and look to the amplitude of the Gaussian, and plot the amplitude of the Gaussian as a function of sine squared psi. So as a function of orientation angle of the lattice plane with respect to the high symmetry z-axis. And I see it is not isotropic. It is anisotropic. It's a strain ellipsoid because they fit a straight line. That means in the z direction, 0, 0, 2, we have a larger expansion due to that bump making process than in the A direction or AB plane, which is symmetric similar. In between, we get the values in between. So we worked it out. The bump is due to that phase transformation, the precipitation of aluminium 12, magnesium 17, where we get a change of composition because aluminium goes from the matrix into the precipitates. Sorry. And a change of aluminium concentration is well known to give a change in lattice parameter, and therefore we see the change of lattice strain in these plots. Okay, let me give a quick conclusion on the magnesium AZ31 material. So the as received sheets, they recover. We don't have grain growth. Thermal expansion is fully linear. There's no phase transformations on the experimental time scale. And this is due because diffusion paths are very large. By thermodynamics, by the phase diagram, you should get precipitation of the intermetallic phase. However, I assume the material has been quenched from high temperatures during the processing, during the making of the material before we received it. And then we heat it up. And in this heating process, there's not enough time for diffusion to precipitate. And this is different in the HPT processed material. First of all, it recrystallizes. during recrystallization, there's a lot of changes going on in the lattice, a lot of vacancies and high diffusion rates. The stresses reduce. We get the grain growth, and the thermal expansion has a bump, which is due to the aluminium 12 magnesium 17 intermetallics. And this bump is anisotropic, as the symmetry of hexagonal system allows. We can go more into that. There's also anisotropic diffusivities having been observed by as late as Schumann in the 1960s, and other anisotropic effects. So only the thermal expansion coefficient itself is isotropic by coincidence, but the other parameters or the other quantities, they are anisotropic, as they should be, more as they have the freedom to be. In the HPT process material, we have short diffusion lengths and a high driving force. Okay, I was confused at the beginning because this is my introduction here. This is the introduction I wanted to give at the first slide, namely that we work here with modern diffraction methods and we exploit neutron and synchrotron methods that you have seen already, and we do a lot of studies in situ and time resolved and multidimensional with the detectors. So I threw myself a little bit into the cold water because I messed up my slides. I really apologize for that. But the important thing is to point out my collaborators. So while I'm at the University of Wollongong, we have the high pressure torsion people, Megumi Kawasaki at Oregon State University, the people from JEA, Japan Atomic Energy Agency, have been involved. And of course, not listed here on this slide, but I have to mention it absolutely, the beamline scientist Ulrich Lehnert and Malte Blankenburg from DESY in Germany, or actually from the Swedish beamline. Okay, that's what we do in situ processing. I went already through many of these features which can be repeated on magnesium AZ91. And there's also the aluminium 12 magnesium 17, which plays a big role, the precipitation, and which leads to anomalies in the lattice parameter. But because time is running, I want to talk more about grain rotation. Can we observe grain rotation? Because I have some exciting news to share here with you. There are grain rotations at high temperature because of grain growth, grain coalescence, and so on. To observe grain rotations, as long as they rotate around the beam axis, then their reflections, they shift on the Debye rings. But if there's a grain rotation changing the Bragg angle, or the angle of incidence to the lattice plane, then we lose the reflection because it moves off the Ewald sphere. And that means the reflections will most probably be lost when they start to rotate. And that results in fluctuations, as I can show it on a monochromatic beam techniques, e.g. on AZ91. But what we need is a technique to follow the reflection in 2D solid angle. And they said, let's use wide beam Laue diffraction. With wide beam Laue diffraction, you can orient the crystal in any orientation. It chooses a wavelength, it chooses a K vector, and reflects. So let's look to grain coalescence. I don't want to talk too much about the technique. I want to talk about grain coalescence. Grain coalescence is a kind of grain growth where neighboring grains, they rotate until they have the same orientation. And then they form a bigger grain. Yeah, if the middle grain here, if that rotates, let's say it has the initial orientation 1, it rotates by the angle omega into the orientation 2, which is parallel to the neighbor grain around Roman Arabic one. Then this forms a new or a big grain, a bigger grain. Then we have grain growth by coalescence. However, the grain has an irregular shape. The grain is embedded in a matrix. It's like a nut in a spanner. Yeah, you do oil mechanics, you have a spanner and you have the nut. You can rotate the nut, and that's how you fix a nut on the screw. So if the grain is like the nut and the matrix like the spanner, then the corners, they would prevent grain rotation, grain or reorientation. Unless I get mass transport. And we know at high temperatures we can have diffusion. Diffusion can transport mass. So we have these pink areas which have to be moved to the greenish areas by diffusion. So normally grains grow in a self-similar way, but abnormally some individual grains grow much bigger than others. This is well known. The grain growth coalescence and abnormal grain growth says it is assumed to be erratic. Its initiation remains an unresolved issue in modern research, and it lacks any simple experimental approach to show how such research should be conducted. These are citations or extracts of citations of these papers given here by famous people working on abnormal grain growth. So let's try this wide beam Laue diffraction. The conception with wide beam Laue diffraction, however, is it is not suitable for powder diffraction. So not suitable for polycrystalline material. And why? From a single crystal, I get this colorful figure here. This is silicon, yeah? So we get reflections due to the orientation of that one crystal, a single crystal, yeah? One crystallite or one crystal. There's only one crystallite in a single crystal. However, if we get polycrystalline material, then from every grain, we get intensity somewhere onto the detector. That means we only would get a halo of distribution, which is the convolution of crystallography and reflectivity and the wavelength distribution of your incoming beam, if it's not completely white. So the idea is now, as we know, the powder diffraction rings, they become spotty. These wide beam Laue halos also should become spotty. And I got very bad grading for these proposals when I submitted them to the facilities work. But we did the experiment at Spring 8 in Japan. So this is the energy distribution. And this is the results. These are movies now heating up the material from room temperature to high temperature. We see already there is a halo. This is magnesium AZ91. So there's a halo of many reflections from polycrystalline material. This is not ultrafine. This is maybe 10 micrometer grain size. And what happens if we go to higher temperature? So this is at the beginning, not at the beginning, this is already at 537 Kelvin, but not much has changed until there. But we go to 586 Kelvin, we see there's a lot of coarsening. And we go further, 636, the coarsening continues. 710, yeah, less spots, more coarsening. 760, there is a halo, but a lot of coarse spots. So the spots are not that fine distributed as at the beginning, because we have less grains in the illuminated volume. And here becomes less. And then cooling, this is highest temperature, 773 Kelvin. And then we cool, we get these streaks. And the streaks, they are the reorientation strains, because we get precipitation of a second phase again, this aluminum 12, magnesium 17, and different thermal expansion coefficients giving stresses onto the grains, and therefore we get the reorientation strain. I don't have time to escape to the movies, but I have a few here. First of all, if we look to the average intensity scattered into a small solid angle, a selected solid angle, so just some area on the detector, then we can see there's evolution. And all these features we can match somehow to the processes or the phase diagram. So here it's a kind of a recovery. Here is a phase transformation, 633 Kelvin, and 710 Kelvin, we go through a eutectic reaction, and then we see intensity goes down because a lot of grain grows, and then we go into dynamical theory of diffraction and things like that. As we cool, intensity goes up again because of distortions. So now I want to show you the observation of grain rotations. I think my time is soon over, right? I try to be fast.
Please take your time and explain as nicely as you already do.
Thank you. So what we see here, this is a movie now at 773 Kelvin. We hold the temperature. We see there are all these spots from the polycrystalline material, but a few spots are moving. And a few spots are going wild. You see them? So here they're going wild and zigzag. Let me put these frames together in color. I don't see the color because my Zoom stuff is in front. But there's this, you see the gradient, green is in the middle and last is red. That means this grain here starts, or this reflection starts from the bottom, if you see my mouse pointer, and then it moves this zigzag way here until there. And another one, it's not a continuation of that one, I worked it out, but another one starts eventually here to move, and then it goes this zigzag way, this and that. And there's a reflection of that same grain which goes this zigzag way. So somewhere to the up. I'm not that accurate here with the mouse. So these grains, they move and they go, they reorient, the reflections they move, the grains reorient. Only a few of them reorient. Most of them remain static in the matrix. Here we look to other detector which zooms in a little bit. What we see there, I put it onto the color time scale again. There are two grains. One grain is coming from here, moving down. orientation moves down, the other orientation moves upward, then they stop, they move together, they coalesce, and eventually they escape together. So you can see that here at the beginning. Here, the two grains, they come together. I put it there in the static images. So I extract the images, A and B. You see they move together. Eventually they hit each other. They coalesce. They become one spot. They stay there for a while in orientation space. And then they run away together. So the one grain continues rotation. The one bigger grain, A plus B, continues rotation. Or here, you have this fat guy going through reciprocal space here. I have to do it again. You see here, the guy moving in zigzag. A very strong reflection, moving in zigzag. So I put it in a color space, color trace. At the bottom, we see the grain moves in here from the top, and then we see the very serrated zigzag way it goes. And this is a strong reflection. That means strong reflection comes from a big grain. So it's not a small grain reorienting here. Now let's discuss it. Sarash and Aspi, they talked about corrugated grain boundary sliding, which is shown here on a linear scale. So we have a sinusoidal variation of the grain boundary, so up and down, it's corrugated. And if it wants to slide, then I have to have mass transport from the front to the back, or from the back to the front, depending on which orientation you move. Then Harris et al., they did the same model on a rotational coordinate system. So this is already the grain reorientation as needed for grain coalescence. So here he shows as a function of orientation angle, theta over pi, it goes, or he makes this zigzag potential as a model for the grain. And finds out that the rates of rotation, so omega dot, the speed, the rate of rotation, is proportional to the stress, shear stress tau, so the torque in this sense, times the mobility of the radius. Mobility of a grain with a radius big R. And if you plot big R here, or R over some critical, then you can see it goes down quickly. That means in their model, the rate of rotation for large grain goes down quickly. So Moldovan, 2002, they say the scaling behavior of grain rotation induced by the grain growth is due to the mobility, which is some constant divided by the radius to the power of p. And that p is 4 or 5, respectively, for grain boundary and lattice diffusion. So probably you have grain boundary diffusion, then becomes 4. P4 means doubling the grain volume scales down the mobility to 40%. And changing the grain volume by 1 order of magnitude scales down the mobility to 5%. However, what we observe in our data is we observe that even large grains rotate for a long time. and even in zigzag orientation pathways. So now I come with my model. The model is that at some place, the grain boundary becomes activated, becomes active, kind of melts there. And then I have a lot of diffusion, grain boundary diffusion. It opens up diffusion channels, and there's literature behind that. And these diffusion channels then allow to rotate, to reorient the grain, at least in this area. But the torque, or this diffusion activated area, can now expand to all of the grain boundaries around the one grain, so to all the boundaries to the neighbors of the one grain. And then the grain can rotate. Boundaries are activated and can rotate. It has a torque now. So this orientation 1 has an attractive torque, let's say, to that orientation 1. But as it rotates, it may now think, okay, in this configuration, halfway through, I get a better torque with grain number 2. So I have a competition of grain Arabic 1 and Arabic 2. This one and that one. Means the grain first orients towards grain number 1, then grain number 2 takes over, and the reorientation goes towards grain number 2. And that makes a zigzag path. And then you have the competition with all the other grain boundaries and all the other neighboring grains until coalescence. And once you have had the coalescence, you still have the activated grain boundary. So then the process continues. The process continues because the grain boundaries are already activated, and they'll remain activated for a long time. So nothing with Moldowan's law that a large grain cannot rotate. It rotates because the grain boundary is activated, and it just continues its pathway. So these are the conclusions. I think my time is really over now. What I want to say is the particular grain becomes activated spontaneously, driving the grain into rotation. This necessarily activates all other grain boundaries because it rotates, gets some, and then this area on the boundary can expand. So then the grain can now more or less freely rotate, of course, needs to follow the diffusion. There's competition of torque from the various surrounding grains, resulting in zigzag reorientations and fluctuations. So they can go forth and back. Sometimes they stay around a point, but they just fluctuate. And as two crystallites align, they coalesce, and this is the grain growth. The grain boundaries remain activated and the process continues, breaking down Moldowan's mobility law, remaining active for a long time. And when the grain becomes very big, then of course there's too much competition with other grains. It may not rotate anymore. The grain boundary reorientation slows down, but the neighbor grain has still an activated boundary, and that can take over, leading to clustering of large grains, which is often observed in these materials. Okay, I may leave this just online, that we use novel technique, wide beam Laue diffraction, and better come to the questions. Thank you for your attention.
Thank you very much, Professor Klaus Liss from Wollongong University.
Thank you.